Hey everybody. So I didn't get a chance to get these videos done yesterday. I apologize, but I'm going to get them done here for you. It's Saturday night, and hopefully you'll have time to watch them on Sunday in case you need that help on your homework. So I'm going to do three things for you in this video, and I'm going to largely just sketch the solution. I'm going to show you how it can be done. I'm not going to plug in any numbers. You guys are competent at doing that, so I don't think that's going to help anything, and it would just delay me getting this video out to you. Okay, so let's start here. Example 2, we've got, it says find the force on the charge Q2 particle. So there's a given charge for Q2. You can see there's Q1 down there. All right, and then sigma is given. And that sigma, remember, sigma is a surface charge density. So that has to do with the sheet of charge that's there on the left-hand side, okay, as you're looking at it. And so our way to get to this, to crack this nut, is going to be that we have to first figure out, let's call it E1 here, okay? And then there's going to be a force from that electric field, and E1 comes from Q1. But then also there's an electric field moving this way, and let me just call the I'll call it ES for sheet, for the sheet of charge, and it is heading that way. Okay, now it's actually the easiest one to calculate. All right, all we have to do is check out our equation right down here. Okay, and so what we would end up there with is sigma over 2 epsilon naught. Okay, and then we would plug in our numbers. All right, so we'd have 8.5 e to the minus 9 over 2 epsilon naught, which is the 8.85 number. Okay, and we would calculate that, and that would give us some value. So, and it happens to be in the positive I direction. Okay, so let me just call that stuff right there, I'm just going to call that ES. Okay, so whatever that number is, that would be ES. Now E1, okay, that's from a point charge, and so I'm going to use this expression down here. So we're going to have KE Q1 over R squared. Okay, and so then we'd plug in our numbers. It's 8.99, 10 to the 9th. Okay, and yeah. And our R squared, it's 2.5 centimeters. Remember, it has to be in meters. Okay, so be careful with that. 0.025 squared, and then the value for Q1. Okay, notice it says pico, okay, pico, so that's 10 to the minus 12. Just like that. So that's straight up. So we would put a K on there. Sorry, not a K. That would be the Z direction. Let's put a J on that baby right there. And then let's call this whatever it is. Let's just call that magnitude E1. Okay. So now you see I've got an X component and a Y component. There's an I and a J. And in this particular case, they're very clean. One is only Y, one is only X. So that's kind of nice, because what that means then is our total electric field, all right, is going to be the vector summation of these things. Okay. And in terms of its magnitude, okay, all we have to do is this right here. Okay, and so that would get that for us. Okay, then the force would be Q times E. Okay, now E is a vector. Okay, so it's got a direction. Pythagorizing it this way, E1 squared and ES squared. All right, that gives us the magnitude. Okay, if we needed the angle, then we could just say that the tangent of theta is going to be, what's that going to be? E1, it's the rise over the run. So E1 over ES. So that would get us our direction there. Okay, if we, for whatever reason, if we needed the specific components of force, okay, then what we would do is we would say the x component of force is going to be Q times our x component of the electric field. And in this particular case, that's going to be Q times ES. And if we needed y, it'd be QEY. And in this particular case, that would turn into QE1. Okay. All right. So pretty straightforward, pretty straightforward. And a lot of times these are going to turn out, things will be set up on right angles for you. Okay. And that just, helps make it a little bit easier. Okay. Let's look at another one. Okay, so we're interested in what's happening to Q3. Okay, Q3 is 5 nanocoulombs over there, just like so. And then we got Q1 and Q2. Now, Q1 and Q2 are opposite charges, all right? They have opposite signs. And we know that because we got the little negative sign right in there, okay? So this is actually a dipole, okay? It's a dipole. It's equal and opposite charges separated by a certain distance, all right? Now, just because it's a dipole, that doesn't affect what we're about to do. I just wanted to point that out for you, okay? So, just to help things out here, all right, so Q3, okay, Q2 is actually a negative charge. This is a negative charge, and this one's a positive, which means Q3, since it's positive, it actually feels an attraction this way, okay? So there's electric field going this way. We'll call that E2. On the other hand, Q3, it's positive, so Q1, since it's positive, it it's going to feel a repulsive force, and there's an electric field headed this way. We'll call that E1. Okay, just like that. All right. Now, can you see that things are symmetric? All right, things are symmetric. All right, Q1 and Q2 have the same amount of force. Okay, so for E2, if we were to calculate here E2 x component, it would turn out to be exactly the same here as E1 x component. All right, because all the charges are the same. All the charges are the same. They just have opposite signs. Okay, so those bits are actually going to cancel each other out. So what really matters here is what's going on here with E2y and E1y. Okay, so the electric field at that point in space, if it's right in the middle, which it looks like it is, the electric field in that space is pointing straight up. Okay, so if we can get that y component of the electric field, we just double it, and we're good. Okay, so let's get that. Okay, so I got to get rid of some stuff here. My drawing's going to get pretty yucky in a hurry if I'm not careful. So let me erase. In fact, I'm going to get rid of all this stuff. And there we go. Okay, so I've got point charges. All right, so let's just focus on E3 or E2 here. It's this way. Okay, now let's say we got this angle in here, theta, and if that angle right there is theta, then that means what we're looking for, which is E2y, is going to be E2 sine theta. Okay, so if we can get E2 sine theta, we're pretty good. All right, now how do we get E2? Well, it's a point charge, and so right down here is what we're going to be working with. Okay, so let's say E2 is KE Q2 over R squared. Okay, and that R, of course, is the distance between the two charges. Okay, now when we plug in our numbers here, okay, I'd put in my 8 point whatever number, and I'm gonna have to figure out what the radius is. But when I get ready to put in Q2, all right, I'm just gonna put in 4.5 e to the minus 9, okay? I'm not going to worry about putting it in there as a negative number because negative and positive really refer to direction, okay? Once I make my drawing, I've got my direction, and so I want to restrict myself to simply using the sines and cosines, and plus I, plus j, minus I, minus j as needed, okay? So I want to calculate the magnitude of E2. I've already taken into account its direction with my drawing, okay? Now let's get R on there, okay? So we've got a triangle in here. Let's take a look here, just like that. Okay, it's 12 across the bottom. It's 5 up here. Okay, so do a little Pythagorean work on there, and what you discover is 13. I tried to pick easy numbers. All right, so that turns out to be 13 there, like that. Okay, so let me get rid of these little side bits here. We don't need that information. We got it. Okay, so we're 13 there is what we want. So up here in our equation, then we are going to divide by 13 centimeters, so 0.13 squared. Okay, 13 centimeters there. All right, and I didn't bother to write in the value for K. You can look at it right down here. All right, so there's E2, okay? Now, what we need is E2 sine theta, okay? Just like that. So what I'm going to do, so I'm going to put this back in here, put my triangle back together here. 5 and 12. Okay, so we could come through here and we could figure out what the actual value of theta is, okay? So if we were going to do that, what we would do is we'd come along and we'd say that sine theta is equal to the rise, the opposite over the hypotenuse, which is going to be 5 over 13 in this case. And then we could calculate what the value of theta was. Okay? So then what we would do on our calculator is we would put in the sine of the angle. Well, okay, you see what's going to happen here? If you put in the sine of that angle, the answer is going to turn out to be 5/13. So why bother? Why bother to calculate the angle? We don't need it. What we need is the sine of the angle, and we already have that. Okay. Now, those of you guys who have had statics and who are in dynamics, you will recognize this trick. We use it a lot. Okay. Whenever you got a nice triangle that with good, well-defined proportions this way, it's a great trick. It's going to save you a lot of time. Okay. And so in order to get E2, then E2y, I'm going to take E2, which whatever this number is right up here. So let's just call that E2. And then the sine of theta is 5/13. So there's E2y. All right. And that means then, remember my total electric field, need a new color here, upwards is actually E2y plus E1y, and those are equal to each other, which means it's just 2 E2y. Okay, so if I want my force, then, which is what we're asked to do, then I'm going to have Q times the total like that. So I'm going to have Q. All right. And then we're going to have 2 times E2 times the sine of theta, which is 5/13. And all that's going to be in the J direction. Okay, just like that. So what you should do, okay, you should take a few minutes and kind of go through this again, start at the beginning and say, what difference would it make if both charges, Q2 and Q1, had the same sign? All right, in other words, what if this was positive and this one was positive? How would that affect the arguments we made about different bits canceling each other out? Okay, how is that going to change it? Okay, so go through that. All right, you don't have to run the numbers on it, but just kind of convince yourself that you can do that. All right, that'd be a really good exercise for you to do. Okay. All right, now I want to look at one more scenario, which is important to your homework. Okay. There's some homework problems on there that are actually you're gonna have to do a little throwback to last semester. Okay. A little throwback to last semester. So let's take a look. This is not, I don't care about this. I just want a blank page. Okay. So there are some problems about having 2 charges. Here's one and here's one. Okay. All right. And if they have the same mass, M and M, and a certain amount of charge, Q and Q. Okay. Now they could have different masses. They could have different Q values. That doesn't really matter. Okay. Those are just details to be worked out. All right. I want to show you sort of the principle of how you're going to go about this. Okay. And so the way you do this is you have to think about the forces. Okay. So since the 2 little bits are pushed apart, the Q's have to both be positive or both be negative. Okay. Which means we're going to have a force this way from the electric field. Okay. But we've also got weight here, mg, and then there's going to be some tension here, T. Okay. Now, there's also some angle theta there, which is also this angle right in here. Okay. So if we make a free body diagram, we haven't done that in a long time, have we? If we make a free body diagram, okay, on our particle, then we've got our tension up here. Okay. This is our angle theta. Here's mg. And there's the electric force, Fe, which is Q times whatever the electric field is. Okay. And then we use our point charge to kind of figure out that distance. Okay. So that's going to depend on this whole distance across there, like that. Okay. Now, what this means is there's obviously there's some tension here. It means that if we look at the vertical forces, okay, Ty is mg, okay, and Tx is Qe, okay. Now, if we divide those two things, all right, Ty is T, in this case it's T cosine theta, because the theta is off the vertical, not the horizontal. So the y part goes with the cosine. So don't let that throw you off there. It's a little bit, we don't usually do it that way, so it may seem a little odd to you, but don't let that trouble you any, okay? And then here's the T sine theta. Now, if I divide these two equations, okay, I'm going to have mg over Qe is equal to cosine theta over sine theta, okay? Just like that. And that's actually 1 over tangent. We could call it cotangent. Sure, we could go down that road. But, I mean, really? Cotangent? Who wants to go there? You know what I'm saying? Okay. So now you can see. Let me rewrite it just a little bit for you here. So mg over Qe is 1 over tangent theta. And now I have an equation that relates mass, charge to tangent theta. Okay. The thing I don't have in there yet is information about the electric field. Okay, and the electric field is going to be K, Q. Oh, I see, we better put some numbers on here. That's Q1, Q2. So this is Q1, this is Q2. All right, over R squared, like that. But I think they're the same. Yeah, let's assume the masses are the same and the charges are the same, or it just the algebra is going to get really nasty on us. Okay, so we'll assume that's the same. Okay, so if we put that expression in for our electric field, okay, what's going to happen? It's going to get a little complicated first. All right, so we're going to have Q, but now my electric field is K, Q over R squared, like this. It's 1 over tangent theta. All right. So I got a Q squared in there now, and I got R squared. My R squared's in the denominator of the denominator. It's got to come back up on the top. All right. So I'm going to have mg R squared over, that's going to be KQ squared, like that. Okay. Now, the last thing we have to deal with is the fact that R here is 2 times the length times the sine of theta, where that's the length of this string. Okay, so we would want to substitute that in. So now I've got mg 2l sine theta squared over KQ squared. Okay. Anywho, it looks a little bit messy, but it's really not that bad. Okay. But now I've got a way to relate all those variables together. Okay. Now, if you've got some numbers on this thing, you certainly do not need to keep it all algebraically like this. Okay. Because the algebra, it's handy to use, but, you know, let's be honest, sometimes it can become unwielding. Okay, and so some of these, you know, you can combine some things together, all right? You could calculate R if you wanted to. I mean, nobody cares. You could get a number out of that thing if you wanted to. Mg is just a number, K is a number. Okay, so there's some things you could do to make this a little bit simpler if you wanted to, okay? But the main thing I wanted to kind of give you a heads up about is you're going to have to go back and think about free body diagrams and equilibrium. Okay, free body diagrams and equilibrium. All right, but hopefully that'll kickstart you on that one. Okay, and anyway, hopefully you're all equipped and ready to go with these things. Okay, there we go.